you don't realize that, but the light is actually bending up away. It's bending. The edges are actually, it's going up away. So it's going up. Here, like this simulation I have here on my screen. I don't know if you can see that, but see those yellow lines at the bottom there? Like I have, like, let's say I'm standing at the South Pole. Let me bring this down here. I have these yellow lines showing that the amount of bending is actually going to be bending. You know, it can't bend more than the curvature of the Earth. It has to bend more. I'm sorry, it has to bend more. It can't bend less. And so it's bending up toward the center, toward the celestial sphere in the center. See how I created this kind of like this upside down lampshade, basically. That would define your horizontal edge. And so it's always going to like bend up to the center there. So like if you're standing down below here at the South Pole, you're going to see the sun just doing, you know, this is like at the time of the equinox. It's just going to stay right at the horizon all the way throughout, like that. The light is always bending up.
I am seeing the way you project sunlight coming out of your tetrahedron onto the glass. I am seeing something like that from the high altitude balloon footage, but that's about it. Like the only thing I can kind of say that I'm seeing for myself is the way that the sun seems to be kind of bent a little bit. It's not perfectly round when you're looking at it from these balloons, you know?
Yeah, at the edge, at the horizon, it's going to bend like that.
It's a little bendy. It's a little bendy.
It's going to squish. It's another indication that you're inside. But this is like your field. This is your field of vision. So you can't see the other side of the Earth because your eye is always going to go to the center. So this is going to define your boundary. And that's why it gives the appearance that you're living on a ball, or the appearance that the horizon is flat. Because laterally, you know, it's going equally in all directions, so it's going to appear flat like that.
Steven, like, can you see my screen right here? Like, now we're looking straight ahead for some curvature. Let's look left or right. Are we seeing concave or convex ball math curvature?
That's what I tried to tell you. I'm trying to explain that to you. You're not going to see the curvature at the horizon level.
We're not seeing it left to right on any axis.
Because radially, the light is going to be bending equally in all directions radially. So it's going to give the illusion of a flat horizon.
I have a question. On a concave model, I mean, I'm just wondering, like, optically, if it was actually the Earth on a concave model, would it basically be a camera upside down with a wide-angle lens, basically? Because wouldn't that make it
Well,
convects?
the way the light actually works within the Earth, just think of it in terms of like the direction of light. And so what I'm saying is that like if you're at like 1,000 miles high with like the Himawari 8, and it looks, and you can take a picture of the Earth, it looks like a convex ball, but it's deceiving because obviously I told you before you wouldn't get that short of amount of time when the sun is supposedly behind the Earth, but also the light is actually going like it's going out toward you, away from you, I'm sorry, and then it's bending up away from you. And so it's kind of like curling back like that. And so that's why we get the darkness. So like if you go up high in a balloon and you see, obviously when you go above the ozone layer, you have darkness. And that's because the direction of the light is actually curving up. And so once it gets to a point where there's no particles in the atmosphere, nothing to reflect the light, just like when you shine a laser up into the sky, into the night sky, it's going to stop abruptly because there's no particles after a certain height. So that's what's happening too when you ascend like that. When you see the edge of the Earth, it's just simply the light bending up like that, and there's no particles for it to reflect off of. That's why we get the blackness.